W-algebras, and W-algebras are is another name for vertex algebras that have fields of higher conformal weight. And over the last 5, 6, 7 or many years, they have often appeared in 2D, 3D, and 2D, 4D correspondences. And the features of these W-algebras that appear in these correspondences are quite new and very interesting. And this talk is about two such features. One of them is triality, which appeared in the story of vertex algebras at the corner of Davide Gaiotto and Miroslav Rabczak. And this is probably a fairly well-known story. And then there's a second one I'd like to talk about, which I like to call the UROT, or translation of W-algebra property. And this has appeared prominently in the story where VOAs appeared as invariants of 4 manifolds by Boris Fagin and Sergei Bukov. And I plan to split this talk into 3 parts. So first I will just give a light introduction, and then I'll come to these 2 problems. And so vertex algebras are the mathematician's name for the symmetry or chiral algebra of a 2-dimensional conformal field theory. And so as such, since these 2-dimensional conformal field theories describe the worldsheet of a string propagating in space-time, they appeared quite prominently in string theory. Now, from a mathematician's point of view, you would say understanding a conformal field theory is more or less the same thing as understanding the representation theory of the underlying vertex algebra well. So this means the VOAs appeared first in the 1980s, and they at the very same time appeared also quite meaningful in mathematics. And namely, at that time, one of the important problems was the monster-moonshine conjecture relating the monster group with modular functions. And it turned out this moonshine conjecture could be proven using the bosonic string construction associated to a very special vertex algebra that had this special group, the monster group, as automorphism groups. And then besides this special problem, VOAs became quite important for mathematics because the representation theory, as we heard in Shu Heng's talk, are modular tensor categories. So they are very nice tensor categories that, for example, give rise to the topological field theories and other structures. And in generality, VOAs are somehow a nice black box that connect to very interesting geometry, topology, number theory, and also other mathematics. And this has continued, but in the last year, it was not string theory that was so much in the focus, but more of a 3-dimensional and 4-dimensional gauge theories. And the shift of type of VOAs we are interested in has changed. But while in the old times, one usually has been looking for unitary, rational, conformal field theories, so that they have this nice modular tensor category as representation theory. Everything is nice and well structured. Now, the modern VOAs have much wilder representation theories, not semi-simple anymore, not unitary anymore, not necessarily finitely many simple objects. And also the type of questions we are asking about vertex algebras are very different. And this talk is about 2 of these new appearances and new features of vertex algebras. And so all vertex algebras I know are associated to affine Lie superalgebras. What this means is the very basic, if you wish, vertex algebra that you can construct is you take your favorite Lie superalgebra, and then then you go to the affinization and you get a vertex algebra or vertex superalgebra. And then there's a set of standard constructions that you can iterate, and all known VOAs you get by an iteration of this standard construction, at least all the ones I know. And these constructions are, for example, extending the vertex algebra, or taking invariant subalgebra invariant under some group, or with the action of another vertex algebras, or something like BRST cohomologies. And we will actually talk in this talk, be concerned with a mix of these constructions. In this slide, I recall some basics about a vertex algebra associated to a Lie algebra, or more general, to a Lie superalgebra. These are called affine vertex algebras, and they are associated to a Lie superalgebra and a bilinear form. So usually you normalize this bilinear form in the standard way, and then consider multiples of this bilinear form, and the multiple is called the level of the vertex algebra. And these vertex algebras are strongly and freely generated by fields associated to a basis of the Lie superalgebra with this operator product algebra. And now usually you don't, then there's a universal VOA, which is called VKG, and this doesn't need to be simple, and then often or usually you pass to the simple quotient. In the old literature, people usually have been concerned with the Westermino-Witten theory, which is the case when this integer is, when this level is an integer, this scaling of the bilinear form. Now, once you have a vertex algebra associated to a Lie algebra, a Lie superalgebra, there's a very nice construction which gives you a zoo of more such structures. And they are associated again to your Lie superalgebra, and then to a choice of a nilpotent element in G. And then it turns out that there exists a complex. That means there exists a ghost superalgebra, just a bunch of fermionic and bosonic ghosts that are specified by the choice of nilpotent element, such that the affine vertex algebra times this ghost superalgebra is a complex, and the corresponding homology is called the W-algebra associated to this Lie algebra and this nilpotent element. This includes the affine vertex algebras. That means this includes the vertex algebras that are associated to Lie algebras. Namely, you just take the zero nilpotent element. The one that most people are familiar with is the principal nilpotent element. So then that's then the usual W-algebra. For example, the usual W-algebra associated to SLN is of type 2, 3, 4 up to n. This means it's generated by one field in each conformal weight 2, 3 up to n. For example, if I take SL2, I just have a single field in conformal weight 2, and this is the Virasoro algebra. And historically, if you look at the literature, people have almost exclusively been concerned with these principal W-algebras, but modernly, this is not the case anymore. Nowadays, we are interested in all these W-algebras, and actually also superalgebras. And not only, of course, the W-algebras, but also their modules, and they have actually very rich and interesting representation theories. I'm not at all talking about this. I'm only introducing here the very basic class of modules. So what is the basic class of modules of a Lie algebra? That are their integrable representations. And so what can I do? I can lift these to a module to the affine Lie algebra. These are then called the while modules. So what I do is I take the integrable representation, the finite dimensional representation of my Lie algebra, and I just let all positive modes of the affine Lie algebra act as zero, and then let the negative part act freely, and then I get a module that is called the while module. So it just has as its top level this finite dimensional representation of the Lie algebra, and then freely induced by the negative modes. And only this type of modules we are concerned about in this talk. The category of these types, and then if I have these modules, I can of course also look at the corresponding homology, and this gives me automatically a module for the W-algebra. So these are these modules, and I will just denote them by m psi f lambda, which encodes all information about these modules. So lambda is the highest weight of the Lie algebra which it comes from. Psi is the level shifted by the dual Coxeter number. This is a notation coming from physics, which is enormously useful, I find. It's, F indicates the nilpotent element. That means which W algebra we are looking at. And I denote the category of those modules, or better, the category whose simple objects are these modules, by KL. And then with these indices, where KL stands for Kashtan-Lustig. Why? Because Kashtan-Lustigs were the ones that prove that in the case of F equals 0, in the Lie algebra case, that this category has actually the structure of a ribbon category, of a braided rigid tensor category. And this is a statement that you actually believe to be always true, or at least for generic level to be true. But it's one of these statements that are very hard to prove, and you actually believe much more to be true. If you actually believe that which F I put there, all these categories are ribbon equivalent. This is a conjecture that nicely connects to quantum geometric Lang lengths, and but we will not talk so much about this in this talk. Then, so the W-algebras, they are constructed as a cohomology or a homology. And this is one way of how I get out of a given vertex algebra a new one. And another way is the coset construction. I just take a large VOA, let's call it V. I take a subalgebra W, and then the subalgebra of that commutes with W is called the coset VOA. In physics, it's usually written as a quotient V over W. And what is interesting is that these cosets can also be realized as relative semi-infinite Lie algebra cohomologies, at least when the scalar, this level, is generic. And this is I view it at least as the mathematical formulation of gauged Weston-Witten models. And so yeah. Now, in this talk, I'm interested with our Lie algebras of interest are of type A. This means they are of type SLN or of type SLN/M. And the nilpotent element we are interested in is called Fn, M. So it turns out that nilpotent elements or equivalence classes of nilpotent elements in SLN are parameterized by partitions of the integer n. And so here my integer is n plus m, and I take the partition n plus m is equal to n plus 1 plus 1 plus many ones. If you view this as a Young diagram, then this is a small hook, one column and one row. And then there are a few special cases. Of course, you can take m to be 0, then this is just the partition n is equal to n, which is the principal nilpotent element. So in this case, one gets the normal, the usual W algebra of SLN, the Wn algebra. If you take m equals 1, you get the W algebra that has been studied a lot by Boris Fagin and Alyosha Semikhatov. So it's often called also the Fagin-Semikhatov algebra. If you take the other extreme case of n equals 1 actually, then you get the affine vertex algebra, and then another maybe relatively well-known case is the case of minimal W algebras. Minimal W algebras are those which only have fields in conformal weight 1, 3/2, and the Virasoro field. So this is maybe as a summary, the type of W algebras we are interested in are associated to SLN, and the nilpotent element is a small hook, the Young tableau that has one column and one row. And the same type of construction also works for the super-algebras. And again, we can, in this case, the nilpotent elements are parameterized by superpartitions. So that means if I look at SLN/M, means super trace with n plus m times n plus m matrices, then any partition of n/m gives me a nilpotent element in a corresponding W-algebra. And we are interested in the ones for, of partitions of this type, namely that n/m is of type n/1 and then only ones. And again, we have a few well-known cases: principal W-algebras, principal W-super-algebras, affine vertex super-algebras, and minimal W-super-algebras. Now, while the principal W-algebra of SLN has generators in conformal weight 2, 3 up to n, these W-algebras all have the property that they also have fields of conformal weight 1. That means they have an affine vertex algebra, subalgebra. And the setup is such that all these examples for the superalgebras as well as for the Lie algebras have a subalgebra and affine vertex algebra of type GLM. So this because we have m ones appearing here in the partition corresponding to the nilpotent element. So this means they have an affine subalgebra, and this means I can take the coset. I can restrict to the subalgebra that commutes with this W-algebra. And I just give them some names, C psi of n, m for the cosets coming from the W-algebras, and D psi n, m for the cosets coming from the W-super-algebras. And don't worry about these special cases. It's just if I take m and or n to be small, then the construction is a little bit different. This is not important for the case. The important thing is the generic case, which is the top one in each of the two. Okay, so why did I do this introduction? Well, of course, I did it because these algebras appear very prominently in one 2D, 4D correspondence. And more generally speaking, the correspondences, at least where I get my intuition from, are AGT correspondence, which is a correspondence between n equals 2 supersymmetric 4D gauge theory to Toda field theory. So Toda field theory is a conformal field theory that has Wn algebra as symmetry, so the principal W algebra as symmetry, and then actually the central connection in this talk are the corner VOAs of Miroslav Rabczak and Davide Gagliotti, and so they appear in the connection to n equals 4 supersymmetric 4-dimensional GL twisted gauge theories. And then also, these also appear in the story of Boris Fagin and Sergei Gukov of VOAs and 4 manifolds. And all these connections of VOA to, so in all these stories, the vertex algebra and also its module category or other invariants of the vertex algebra appear as kind of meaningful invariants of the gauge theory. And this is a general theme. The VOA is a 2D thing, so a VOA is of course much easier to understand. As a 4-dimensional gauge theory, it's still very difficult to understand. And so if I can make progress in my understanding of the VOA, of its representation theory, or other properties, then maybe this will teach me something for physics. I will now, I'm concerned with the converse. I'm taking predictions from physics and I'm trying to understand them in a vertex algebra setting. And the vertex algebras of interest are the Y-algebras that were introduced by Miroslav and Davide, and also studied a lot by Miroslav and Thomas Prochaska. So these are called Y-NML algebras, where NML are non-negative integers. And then there's also an index psi, which is the coupling of the gauge theory. And they appear at the junctions of interfaces in these four-dimensional gauge theories. And on each, and the associated gauge groups are UN, UM, and UL. So here we take gauge groups of unitary type. There's a very similar story for gauge groups of orthosymplectic type. It's a little bit more complicated. And then it's not only the VOA that is associated to the setup, but then the line defects on the interfaces are associated with, so you think about it as modules are associated to the line defects, and these line defects categories, it makes sense to call them Kashtan-Lustig of n/m, meaning Kashtan-Lustig of SLN/m, whatever this is supposed to mean. And then one can have webs of Y-algebras, and I will give you some pictures before I go on. So this is my drawing of a Y. You just draw your Y, and then each face you label by an integer, n, m, and l, and each line segment you label by a category, and this category you give the name Kashtan-Lustig, and then first integer, the integer on one side / the other one. The way you think about it is that this YNML algebra is some very new and complicated vertex algebra that has three each other centralizing categories as categories of modules, namely somehow categories associated to the Lie superalgebras n/m, m/l, and n/l for some level, which I omitted here in the picture. And the picture for the for the web is you just connect many Y's, and then and again do the labeling. Each phase is labeled by a non-negative integer. So here n, m, l, r, s. At each corner you have a corresponding Y algebra, where the indices are the corresponding integers, the corresponding gauge group labels. And then to each line segment you attach a category. And the picture is that, so now naively you might maybe think the vertex algebra you associate to it is just the tensor product of these three Y algebras associated to this corner. But these Y algebras share common categories, and then you can extend along them. So this means a web configuration like this one has a large extension of the tensor product of three Y algebras. And now you see why did I introduce this coset algebras, this coset of the small hook W and W superalgebras, because they are Y algebras where one of the labels is 0. So this means that the Y algebras, we call that the C psi was the coset by the affine GLM subalgebra of a hook type W algebra of SLN plus M, and the D psi is the GLM coset of a hook type W superalgebra of the Lie superalgebra SLN/M. And so essentially these cosets are the Y algebras up to tensoring with a single free boson. Okay, let me, so if we, in this picture, I said the associated vertex algebra is not the tensor product of these three Y algebra, but an extension of this. And there's a precise formulation of this. So the representation theory of a category of modules is hopefully a rigid braided tensor category. And as long as you can prove that this is actually true, then you have a very nice theory, namely that extending the tensor product of two VOAs is equivalent to having an equivalence of tensor subcategories of these two VOAs. You can extend these two VOAs if and only if they have a subcategory that is braid reversed equivalent. This braid reversed means that you can pair the operators such that they can that the corresponding OPE of the is local. So categorical, I mean the locality of the operator product algebra of VOAs and this extension in these extensions is on the categorical level the same as having a braid reversed equivalence. So what it means, sloppily speaking, and that's a good way to think about it, two VOAs can be extended to a larger structure, to a larger VOA, if and only if they share a common subcategory. And this is exactly what this picture will say here. This Y-algebra and this Y-algebra, they share the corresponding Kashtan-Lustig L/M category. Okay, and this picture of gluing vertex algebras is very, very key in the corner VOA or webs of VOA construction, and also actually in the four manifold story. I now want to spend the rest of the talk talking about two conjectures coming from physics and what we have to say about those. So the first conjecture is the triality conjecture of Miroslav and Davide, which in a similar form has been conjectured before by Garbadil and Gopakuma. And it says that if I simultaneously permute the indexes, the NLM of the Y-algebra, and also transform the coupling constant psi in an appropriate way, then I get an isomorphism of the Y-algebras. That means they have an S3 symmetry somehow. This is from the physics setup obvious, right? Of course, if I have my Y, I can rotate it, I still have a Y. And the question is, how does the coupling change under these procedures? And this is encoded in these formulas. So one key conjecture, one should say, is whether one, I mean, is this actually true for the corresponding VOAs? I mean, can we confirm the VOA predict and the physics prediction? Yeah, can we prove this prediction? And Andy Linshaw and myself, we have a theorem that this is indeed true if at least one of the labels is 0. So if all labels are non-zero, then we can't do the proof because one needs to know too much about representation theory of Lie superalgebras. So this is too complicated for the moment for us. But this theorem says there is a triality of cosets of small hook type W-algebras. That means there's a triality of Y-algebras. And what it says is here this coset of the W superalgebra is isomorphic to this coset of the W-algebra, where the shifted levels are related inverse to each other. So where do we know this? An isomorphism of W-algebras where shifted levels are inverse to each other. This is Fagan-Frankel duality of a principal W-algebras. And indeed, a special case of the statement is the original Fagan-Frankel duality. So this first isomorphism is a large generalization of the well-known Fagan-Frankel duality, while the second one, or better, this one, the inverses of the shifted levels add up to 1. So this isomorphism actually is a large generalization of the coset realization of W-algebras. We will see this a little bit more explicit in the coming slides. Okay, so now you can say, so what, we confirmed a statement from physics. The physics conjecture was very clear. That means there was very few doubt that that conjecture was true. Nonetheless, I mean, of course, it's always important to prove a conjecture, but also we developed quite a few new technology in order to prove this. So because we had to prove quite a few properties of these cosets. First of all, we had to show that these are simple vertex algebras for generic parameter. And the way we did this we studied a large psi limit, which one usually does in order to get some Poisson vertex algebra, but we did a slightly different limit so that we got what we call a generalized free field algebra. And then from looking at this generalized free field algebra, or this limit more generally, we were able to prove the simplicity statement, and also that what are the generating fields of what type are these W-algebras. And then the key step is, so my collaborator Andy Linshaw, he proved that there exists a unique two-parameter VOA of type 2, 3, 4 up to infinity. So it's called the W infinity algebra that has been discussed a lot over the last 30 years in physics. And we can prove that our cosets are one parameter quotients of this one. And we can explicitly determine which quotients these are. So there has been this conjecture by Miroslav and Davide. We can prove it when one of the labels is 0. And then there are a few more conjectures by these people together with Prochaska. Namely, they also expected that this Y algebra is actually a quotient of this W infinity algebra. And they also predicted what kind of, how to characterize this one parameter subfamily nicely. There's a very nice parameterization for it. And they also predicted what are the strong generators of these Y algebras. And all these things we can prove if at least one of the labels is 0. So this is the first thing I wanted to report on. Now we have developed some new technology on how to prove these VOA conjectures coming from 4-dimensional physics. But now, having had this observation, it's of course nice that you can say that a certain coset VOAs are isomorphic. But it's kind of nicer if you, I mean, it's of course nicer if you have a more direct relation. And I think it's very instructive to think about these new VOAs that appear as somehow coming from VOAs that are somehow generalizations of Peter-Weil theorem for compact Lie groups. So Peter-Weil theorem just tells us that the space of function on a compact Lie group is the direct sum of all irreducible representations times their duals. And now let me simply tell you what the generalization is. Now, instead of taking the finite dimensional representations, I take now two affine vertex algebras and take the corresponding induced modules, the Weil modules. And then, and then of course, so this means instead of taking the space of functions on the compact Lie group, I take a corresponding vertex algebra object. That means it's the direct sum of the Weil modules. I sometimes have to add some kind of dummy VOA to make it local. This is not too important. But then I can, of course, also do the quantum Hamiltonian reduction on either the first factor or on both factors. So and this is a conjecture that appeared in my work with Davide, where we simply, where we observed that these types of VOAs should exist, and indeed one can prove in many cases that these VOAs do exist. For example, if I take n equals 2, then this very first algebra is the affine vertex superalgebra of D21 alpha of this very exceptionally superalgebra at level 1. And now one observation is that this triality of Davide and Miroslav is related to these vertex algebras that are tailored after Peter-Weil. And namely, we have this conjecture. If you take this large extension of two affine VOAs of type SLN, you perform the hook type reduction on one of the factors, and then this still has an affine GLM subalgebra, and you take the corresponding coset, then you get a W superalgebra that appeared in the triality. And similarly, if you take one W-algebra in our triality, you tensor it with one of these Peter Weil type VOA extension, and you take the relative semi-infinite Lie algebra cohomology, you get the third type of W super algebra that is involved in our triality. So it seems that this triality of coset algebras holds, but there's a much nicer structure, namely these A of SLN psi algebras, which are direct sums over all our dominant weights and the corresponding Weil modules diagonally paired, and then just applied some standard construction to it. And recall that the coset construction can also be phrased in terms of this Lie algebra cohomology. So I could also have written this first conjecture in terms of this relative semi-infinite Lie algebra cohomology. And Andy and I, we were able to confirm the first conjecture on the level of characters, which was actually enormously difficult because you had to understand how certain multivariable meromorphic Jacobi forms decompose, and they were not of, and so that was actually quite difficult. And we didn't try, yeah, thank you. And we didn't try to prove the character statement for the second one. Okay, I want to spend the last very few minutes to talk about the second W-algebra observation we have. And this gives, so let's first recall that vertex algebras are also nicely connected to geometry via the AGT correspondence. And the main theorem I have in mind here is the theorem by Schiffman and Bassaro that says that the equivariant cohomology of the moduli space of torsion-free coherent sheaves on CP2 equipped with some framing at infinity concerns has a W-algebra action. And nowadays, one is again interested in large generalizations of this. And the best theorem at the moment is due to Rabchak, Soibelman, Young, and Zhao, which is a similar statement, namely that W-algebras called Wn, M, L algebras act on these cohomologies. And the conjecture is that these Wn, M, L algebras are the same as the Y-algebras of David and Miroslav. And if you do this connection to geometry, the W-algebras are realized as some kernels of screening operators, which is one way one usually views W-algebras. And so one has, for this new type of W-algebras, one has also to prove the screening realization, which involves understanding screening realizations of W super algebras, which needs to be developed. So we were able to do this for the very first case. And now the idea of Sergey and Boris is that also the equivariant cohomology of this modular space of G instance on a form manifold has a VOA action, and they observed, and these form manifolds are labeled by VOAs, the boundary components by categories. And the gluing of form manifolds is again corresponds to this VOA extension problem I presented before. Now, what I found extremely striking is the blow-up observation from them. So what they did is they took a form manifold, they removed a small four-ball, and did the same with CP2 with reverse orientation and glued them together on the column S3. Now, to each form manifold, they associate a vertex algebra. So that means they would like to know what is the vertex algebra associated to this glued manifold. And the claim of them is that this is a very simple construction. It's just the tensor product of the original vertex algebra, the vertex algebra associated to the original form manifold, tensored with some object called the urod. So urod is Russian and is not a very polite word, but it's actually a very nice object. And the underlying theorem for the urod, so all I will want to do for the last 3 minutes is to present show you that this statement is very nicely reflected in a property of the quantum Hamiltonian functor. I mean, this statement I like to rephrase as this theorem, saying that the quantum Hamiltonian reduction functor commutes with tensor and with integral representations. So this means I take an affine VUA at level k, an integral one at level n, then I can take the tensor product, and I have the diagonal reduction at level k plus n, or the reduction on the very first factor. Our theorem is that the answers are the same. However, the conformal vector on this integral representation is somehow unusual. And why is this interesting? So the OROT, first of all, is nothing but the integral representation at level 1. Well, this is interesting because the coset realization of principal W-algebras says that if I take my affine VUA tensor with the integrable VUA at level 1, it's an extension of the affine VUA at level k times the principal W-algebra. And now I can apply the theorem that the quantum Hamiltonian reduction functor commutes with integral representation to this theorem. This means I replace this factor by the corresponding W-algebra, and I replace here the highest weight modules of the affine vertex algebra by the corresponding W-algebra module. And the same type of statement holds. So this is a very surprising statement because it tells you W-algebra of type F prime times L1G times this very simple OROT VUA contains an action of the W-algebra at level shifted by 1, hence the name translation, and the commutant is a principal W-algebra. And this theorem should be viewed as a VUA version of the prediction that the gluing of a 4-manifold on a CP2 bar is nothing but on the VUA level taking the tensor product with a very simple VUA, namely the OROT. Okay, I'm sorry that I was at the end a little bit fast. Let me summarize. So vertex algebras, especially W-algebras, appear as meaningful invariants of 4-dimensional gauge theories. And there have been 2 predictions that I found particularly interesting, namely the triality, that means the certain cosets of certain W-algebras enjoy a triality of isomorphisms. And another prediction is that somehow there exists a mysterious VUA, which is nothing but the affine VUA at level 1, so that if I tensor a W-algebra with it, I get an extension of 2 W-algebras. And we were able to prove these 2 types of predictions coming from physics. And it actually turns out that these 2 observations seem just to be the tip of the iceberg of many, many nice things to come. So for example, we are at the moment looking at much more miraculous properties of the quantum Hamiltonian reduction functor, which probably will have many future nice applications. Okay, yeah, let me finish here. Thank you very much for your attention.
Thank you very much, Thomas, for this nice talk. I'm just going to unmute the participants so they can give you a round of applause. Okay, so now we've got some time for questions. If you have any questions, please just raise your hands on the Zoom button, or if you're unsure how to do this, just write into the chat. We've got a question from Faye Key. Please just unmute yourself, Faye, and go ahead. So, Faye, I think you're unmuted. Okay, maybe there's just a technical problem. Something is wrong with his microphone. Okay, do you want to just type in your question and then I can read it out and Thomas can answer it? Maybe while Faye's doing this, I can just ask a question, Thomas. So the way I understood it so far, you are taking, I mean, you're taking the physics conjectures and then trying, you get new predictions for VOAs, which, as you say, difficult sometimes to prove because of the representation theory. Is there anything you can say going the other way? So having developed some of the machinery you have, are you led to any new conjectures you might pose for the physics? You're just muted.
Can you hear me?
Yeah, I can hear you now.
Yeah, this is the nice thing. Yeah, indeed. I have two conjectures which I really like, and I haven't seen them in physics, and they are somehow natural in generalizations of this theorem that I had, that the quantum Hamiltonian reduction functor commutes with tensoring with integral representations. So let me tell you how do you put physics aside, come up with this conjecture. Well, if you for some reason look at these two reductions, you will observe that the super characters of the complexes coincide. And moreover, you have a no-ghost theorem, which implies that the super character is actually the character of the reduction. So this means that this theorem is not coming from nowhere. It comes from the observation that this is already on the level of characters and equality. And having that in mind, you can ask yourself, can I set up more complexes which have the property that their characters coincide? And of course, they also should share more common properties. And for example, Davide and Miroslav have this Y-LMN algebras where all indices are non-zero, and they correspond to other reductions of Lie superalgebras that are too complicated for us. But for example, what I can prove, I just have to write it up, is that the corresponding W-algebra, whose coset is Y-LMNN, has the property that there exists a new type of reduction that gives the W-algebra where every index is reduced by 1. So this means somehow, if you look at it from the physics side, somehow you can reduce the rank of the Lie groups on the interfaces simultaneously by 1, or then actually by any integer. And this seems to be interesting. And then there's a super powerful conjecture, which I call the small reduction conjecture, which so if I take a big Lie algebra G, and I take a nilpotent element that is also nilpotent in a subalgebra, then I can view my big vertex algebra as a vertex algebra of the big type, or as a module for the smaller one. And I can take the two corresponding quantum Hamiltonian reductions. If you look at the complexes, you observe that the complexes differ by a free field algebra, by some ghosts. The statement is that the same is true for the reduction, for these two different reductions. And if that is true, then one gets a mathematical framework to describe the gluing of the Y-algebras very nicely. So this is a very, to me at least, a very important conjecture. Yeah.
Okay, thanks. So we'll have to keep an eye out then for the future work. So they managed to write their question. I'm just going to read it out, and maybe you can answer it directly. So, is there anything known about intertwining operators among representations?
Of these Y-algebras, I assume now?
I assume so. Yes, let's assume this. Maybe Faye can correct if...
Yeah, not much, no. This is unfortunately not. So the main thing we would like to prove is that the intertwining operators between W-algebra modules give us a rigid braided tensor category. And in order to prove this, one needs to verify certain finiteness conditions, which we only managed to do for the Virasoro case for the W-algebra of SL2 so far. So, I mean, this is a totally natural question, and one definitely should study it a lot. Unfortunately, it's somehow difficult.
Thanks. So phase writing, there is a C2 cofiniteness. C2 cofiniteness is a problem.
Yes, I mean, these algebras are very far away from being C2 cofinite. So this is I mean, first of all, it's not easy to show C2. So C2 cofiniteness would imply the tensor category statements. That's why it's interesting. But C2 cofiniteness also implies that there are only finitely many simple modules, inequivalent simple modules, which usually fails for these VLRPs.
Great. Thanks. So then there's another question from Yifan Wang. Yifan, please just unmute yourself.
Hello.
Hi, we can hear you.
Oh, okay. So I have a question about your last slide, point 5. Can you go back to that slide?
Yes.
Right. So you mentioned there's this relation between W-algebras and toric-Clapeyron threefold.
Yes.
So my question is, can you use relations between various W-algebras to try to understand string theory dualities?
And to understand,
for example, there's a, for example, by doing two-duality, there's a brane realization of the toric-Clapeyron threefold.
Yeah.
From PQ5 branes. Is there an intrinsic W-algebra construction there? And can you use that, the relation between that W-algebra and this W-algebra you identify directly from the toric-Clapeyron threefold to understand dualities in string theory?
Yeah, that's a good question. I don't know. At the moment, all I know is, so I think if you give me a toric variety, then and you give me time to sit down, then I can probably tell you what's the corresponding VOA. But then and then of course one can think about I mean look at what we know about this VOA and see what kind of what the isomorphisms that we know about these W-algebras tell us.
Right.
But I can't say anything explicit at the moment.
I see. Thank you.
But it's a very nice game already, how to take your favorite toric threefold, write down the corresponding PQ web, and then you know how to, I mean, then choose your ranks, choose your gauge groups on the interfaces, and then you already have a way to write down the corresponding VOA. But yeah, then how to go on is I don't know.
Sorry, just a follow-up question. For non-toric Clapeyron, this is not possible because you don't have the PQ web description?
The combinatorics here is tailored after the PQ web. So this means for this type, it's just toric Clapeyron. But who knows, maybe there's something beyond PQ webs for the UAs.
But is there like an underlying, I mean, a more general principle that tells you when I have a Clapeyron threefold singularity, Clapeyron threefold variety, I should expect a W-algebra? A more fundamental perspective. I mean, whether this W-algebra can be described in the way that you mentioned, depending on whether the Clapeyron has a toric description or not. But is there a more fundamental principle tells you that you have to, I mean, there is a W-algebra lurking?
Yeah, I don't know.
Okay.
Sorry.
Right. So any other questions? There's another question from Mikola Dedushenko. Please just unmute yourself.
Hi. I just something related to previous questions. What are the challenges when the PQ web has loops? Because I think Miroslav and co-authors only consider trees, as far as I remember.
Yes. Loops would just So the way you think about it is these Y-algebras, they have three hands, they have three categories. And if you do two Y-algebras, you glue them along one category, but you can, of course, if a second one also corresponds, you can also glue along that one and you get a loop. So there's no big problem in that, no. So, yeah, loops are, they fit well into this framework. I mean, yeah. So mathematically, it's hidden in the statement that these three categories that this Y-algebra has, they centralize each other. This means if I do one gluing, then the extended VOA still has this type of category as a category of modules. And that means I can also then glue along a second category and get a loop. Yeah. Okay, if you want, I can explain that in private, maybe in more detail. You don't seem happy.
Nicola, you're just muted, but yeah, maybe given the time, it's best to leave this to private discussion. There's also a comment on the previous question, but yeah, I mean, maybe since we just have only a couple of minutes left before the next talk, it's best to just leave it at this. Thanks again, Thomas, for the interesting talk and for this discussion. And yeah, then we can maybe set up the next speaker. Thanks, Thomas.
Thank you.